Now let's look at functions with discontinuities. In particular, let's given a function, let's identify discontinuous points. So we're going to focus on two types of discontinuities. One is called an infinite discontinuity. And an infinite discontinuity is simply a vertical asymptote. So an example of such a discontinuity would be something that looks like this. You have at some point, some value of x, a vertical asymptote, and then you have a function that looks like this and let this stay. Or another example, you have a function which, it doesn't really matter which way it goes. It could look like this, and then it could look like this. Right? The key is that for some value of x, there's a vertical asymptote. That's the key. The second one is called, they have got different names. Sometimes they're called holes or bubbles. And at that point, that's going to be a point discontinuity. Or sometimes it's called a removable. And the reason it's called a removable is that if you have a function where you could simply draw the function by removing a single point, then that would be an example of a removable discontinuity. So here would be an example here. Doesn't have to be this simple, but you have some function and there's a single point for which the function does not exist for a certain value of x. So here we'd say that f of x has a discontinuity at x equal 3. It could also be a more complicated curve. Another example. You could have something that looks like this, like that, say, right? G of x. The key is that g of x at x equals 1, the function is continuous except at that particular point, so that's called a removable discontinuity. So how do you distinguish between the two? Well, the key to discontinuity, at least these two discontinuities, is dividing by 0. Remember, you can't divide by 0. And let's look at two examples. One example, both factored. So the first example, f of x, would be something that looks like this. X plus 4, x minus 3, over x minus 3. In the second example, g of x, let's say, is equal to x plus 5, x plus 6, let's do x plus 7. In this case right here, one way to think about it is that you can, well, I got to be careful, that if the same term is in the numerator and the denominator, you would be able to cancel these two as long as x is not equal to a value such that you're dividing by 0. So if you think, for example, here, x cannot be equal to 3, because if x is equal to 3, let's plug it in, you would get 7 times 0 over 0. And 7 times 0 over 0 does not exist because that would be dividing by 0. So it turns out that f of x here is equal to x plus 4 if x is not equal to 3. And that's an example of what's called a removable discontinuity. Or sometimes they're just called holes. There's a hole at x is equal to 3. G of x, you still can't divide by 0, but there's no canceling that could be done. So this is simply saying that there's a vertical asymptote or an infinite discontinuity at x is equal to minus 7. Because if x is equal to minus 7, if you plug it in, you would divide by 0. So that's what's called an infinite discontinuity. So an example of a problem would be identify any discontinuities for a certain function. And let's do g of x is equal to 3x squared minus 75 over, let's say, 2x squared. No, let's say 2x minus, let's say 10. So basically what you're trying to find is you're trying to find points where you would divide by 0. That's the key. And the way that we're going to do that is we're going to factor. So the first thing we're going to do is factor the numerator. We take a 3 out. We get x squared minus 25. And then if you can further factor that to 3x plus 5, x minus 5. The denominator, you can just take a 2 out. So you take a 2 out and you get x minus 5 to x minus 5. Now, in a more beginning algebra classes, we would say that we can cancel the x minus 5 and the x minus 5. And you can do that, except for you have to identify that if you do that, you know that x can't be equal to 5. So another way to say that is this is equal to 3x plus 5 over 2 if x is not equal to 5. Because if x is equal to 5, you would have a removable discontinuity, or what we might call a hull. So here you would have, since the question isn't to simplify the function but to identify the discontinuities, this would be your answer. Your answer would be that there's a removable discontinuity. And I'm not 100% sure that's the way you spell removable. At x is equal to 5. Sometimes I'll ask you, what is the discontinuity, and is it removable, or is it infinite? Let's do another example. Let's say you want to identify the discontinuities of k of x is equal to 5x minus, let's say, 35, x squared plus 6x plus 8. Again, you're trying to find out where you divide by 0. I'm going to take a 5 out of the top, and I get 5x minus 7. The bottom, there's a x squared. It's a trinomial. I'm going to try to factor it, x plus and x plus. Now, if I couldn't factor it, I would just use quadratic formula. Two numbers that multiply to 8 and add to 6, that's going to be 4 and 2. Nothing cancels. So here the key is, if nothing cancels, then you know that there's no holes. That's the only way you can get a hole, is when something cancels. So here you're going to have some discontinuities. You're going to have discontinuities at x plus 4 is equal to 0 and x plus 2 is equal to 0. That's x is equal to minus 4 and x is equal to minus 2. Those are your discontinuities, and in this case they're both infinite discontinuities. And let me try to spell that one more time. That's infinite discontinuities. And it turns out infinite discontinuities are just sort of class and types. And that's how you find or identify the discontinuities of a polynomial.